Your boots just hit Martian soil, the hatch sealed behind you, and somewhere back on Earth, a billionaire is posting a celebratory tweet about humanity's next chapter. What he's not mentioning is what happens next. Not the part where you spend 2 hours every morning fighting your own skeleton, not the part where you drink recycled urine for the rest of your life, and definitely not the part where the atmospheric pressure outside your suit sits so low that your blood will literally boil if you get a tear in your glove. None of that makes the highlight reel. None of that gets 50 million views on a rocket landing video. All of that lives in the fine print, and you just signed it in permanent ink. Every colonization pitch shows the same footage: the dramatic landing, the first footprint, the flag, and the speech, and the tearful calls home. What gets cut is everything after. The 10,000 days of slow-motion survival on a planet that's trying to kill you through 47 different mechanisms simultaneously. This video covers what your life actually looks like now, including the air you're not breathing, the water you're recycling, the body that's dissolving, the mind that's unraveling, and the radiation rewriting your DNA while you read the brochure about exciting opportunities in off-world agriculture. This is the fine print, so let's read it together. The first thing you need to understand is that you will never breathe Martian air. Not because it's thin, and not because it's cold, but because the atmosphere runs 95.3% carbon dioxide with only 0.16% oxygen. Earth gives you 21%, and Mars gives you 1/100th of that, which means every breath you take for the rest of your life comes from a machine. The colonization videos love showing MOXIE, NASA's oxygen experiment on the Perseverance rover. The technology works by heating Martian CO2 to 800 degrees Celsius and cracking off oxygen atoms through solid oxide electrolysis, producing about 10 grams per hour at peak performance. And here's what they don't mention. You need 840 grams per day just to stay conscious. That means scaling MOXIE 200 times larger and running it around the clock while burning 25 to 30 kilowatts of continuous power. And that's just for air, and that's just for one person. The power has to come from somewhere, and solar panels seem reasonable since Mars does get sunlight. But Mars also gets dust storms, planet-wide dust storms that can last for months. The 2018 storm started in late May, wrapped the entire planet by June 19th, and pushed atmospheric opacity to 10.8, which meant less than 1% of sunlight reached the surface. The Opportunity rover survived 15 years on Mars, and that single storm killed it in weeks. Batteries drained while solar panels sat useless. Systems went dark, and that was the end. Your oxygen system runs on power. Your power comes from solar, and solar goes dark for 3 months during a global storm. The math gets uncomfortable fast. Nuclear power serves as the backup. Fission reactors that don't care about dust and RTGs that keep humming regardless of what's happening in the sky. If your colony planners installed nuclear baseline power with solar for supplemental capacity, you'll survive the storm sealed inside your habitat while rationing power and watching the sky turn ochre for 3 months straight. If they optimized for the press release instead of the survival math, you'll find out during your first major storm when the oxygen alarm starts beeping, when the CO2 scrubbers start failing, and when you learn that suffocation moves slower than the movies show, but the ending stays the same. That covers the air situation, and we haven't even gotten to water yet. Here's a conversation starter for your first crew dinner. That glass of water in your hand has already been through at least 3 other people. The ISS water recovery system hits 98% recycling efficiency by running urine through vacuum distillation and capturing sweat and breath moisture with dehumidifiers, then pushing everything through multi-stage filtration until the output tests cleaner than earth tap water. You'll be drinking your crewmates' processed bodily fluids for the rest of your life, and the alternative is death by dehydration in about 72 hours. Your standards will adjust faster than you'd expect. Mars does have water ice, millions of cubic kilometers of it, with some deposits running 100 meters thick and buried just 1 to 2 meters below the surface in places like Arcadia Planitia. Purity runs above 80% in some formations, and yes, it's there for the taking. Here's the fine print on extraction. The drilling equipment needs to function at negative 60 Celsius average temperatures, while heating systems melt what you pull up and processing infrastructure purifies the output. All of this needs to work flawlessly in an environment where dust infiltrates everything, and the nearest replacement part sits on a supply mission that's 6 months away. A single Starship return trip requires 600 metric tons of water for propellant production alone, which works out to a ton of ice extraction per day sustained over a full year. That means equipment running continuously while you maintain it in a spacesuit, working in conditions that will kill you in 90 seconds if your suit fails. Your daily water ration comes to 3.8 liters. Back on Earth, you probably burn through 80 gallons. Showers exist only in memory now, replaced by sponge baths, and the particular smell of 6 humans sharing a sealed environment environment with recycled air. Missing Earth yet? We're just getting started, because now we need to talk about what Mars is doing to your skeleton. If you're enjoying my video, please subscribe, hit the like button, and comment below your thoughts on Mars colonization. I worked very hard researching this video, and I'd appreciate any support you can give me. Thanks. You're standing in 0.38 grams, about a third of Earth's gravity, and it probably feels liberating, bouncy, maybe even fun. Your bones don't share that opinion. Your skeleton functions as a living system that responds to mechanical load, and on Earth, gravity provides that load constantly. Mars just cut that load by 62%, and your body's response is to decide that all this heavy bone tissue isn't necessary anymore. Dissolution begins immediately. On the ISS, which runs at zero gravity and represents the worst-case scenario, astronauts lose 1 to 2% of their bone mineral density every month. Weight-bearing bones deteriorate faster, with the femur dropping 1.5% monthly, and trabecular bone, the spongy internal structure, degrades at 2.2 to 2.7% per month. Here's the part the recruitment materials skip over. A 2022 study published in Nature tracked 17 astronauts after they returned to Earth, and 9 of them showed incomplete bone recovery in their tibias after a full year back in normal gravity. Some of that damage appears permanent, with researchers comparing the loss to a decade of bone density vanishing in just a few months. Those astronauts came home to recover, and you're not coming home. You're staying in 0.38 grams for the rest of your life, and nobody actually knows what that does to human bones over years or decades because no one has ever experienced it. You're the experiment now, and this is where it gets worse because your muscles are going too. Without Earth gravity loading them constantly, muscle mass drops 10 to 20% on short missions, and long-term stays without aggressive countermeasures can hit 50% loss. Your postural muscles deteriorate fastest, the ones that keep you upright and stabilize your spine and let you walk without falling over. The countermeasure is exercise. 2 hours minimum, every single day. Resistance training happens on machines that consume precious habitat space, while treadmill running requires harnesses pulling you down to simulate load. Cycling on ergometers burns power you're already rationing for oxygen production, and none of it is optional. ISS astronauts follow this regimen religiously, and they still lose bone, they still lose muscle, and 83% of them can't stand up properly when they return to Earth because their cardiovascular systems have deconditioned so badly they can't maintain blood pressure in an upright position. 2 hours of mandatory physical therapy fills your morning now, not as a choice, but as a requirement for continued mobility. Skip it for a few months, and walking becomes difficult. Skip it for a year, and your bones might fracture under your own reduced body weight. Still feeling good about that one-way ticket? We haven't covered radiation yet, and radiation is where the fine print gets genuinely ugly. Every second you spend on Mars, particles you cannot see or feel or taste pass through your body, and some of them tear apart your DNA on the way through. Earth has a magnetic field that deflects most cosmic radiation before it reaches you, plus a thick atmosphere that stops most of what gets through. Mars has neither of those things. The thin Martian atmosphere provides 16 to 22 grams per square centimeter of shielding, while Earth provides about 1,000. Standing on the Martian surface means standing essentially outside, in space, with a thin layer of CO2 above you that accomplishes almost nothing. NASA's Curiosity rover measured this directly, recording surface radiation doses of 0.67 millisieverts per day. That works out to 245 millisieverts per year, and Earth's background radiation sits at 2.4 millisieverts annually. The difference is a factor of 100, which means you're absorbing 100 times more radiation than everyone you left behind, every single day. That measurement came during solar maximum, when the sun's activity actually suppresses galactic cosmic rays. During solar minimum, doses climb to about 1 millisievert daily, a 49% increase, and the sun's 11-year cycle guarantees you'll experience both conditions. A complete Mars mission covering transit there, surface stay, and transit back delivers approximately 1 sievert of total radiation exposure, which represents the European Space Agency's career limit for astronauts and correlates with a 5% increased lifetime cancer risk. You're not doing one mission and going home. You're staying permanently, which means the radiation accumulates year after year with no reset button. Habitat walls provide some protection, and water ice shielding can cut exposure by 50% or more. But you cannot stay inside forever. Equipment needs maintenance, ice needs extraction, and systems need repair. Every EVA adds to your cumulative dose, while solar particle events spike radiation 30% above baseline during major flares. Your habitat needs a storm shelter, the most heavily shielded compartment available, where you'll retreat during these events and wait while watching dosimeter readings, and knowing that even the shelter doesn't stop everything. Calculating exposure budgets becomes part of daily life now, weighing every outdoor task against its radiation cost and accepting that your statistical lifespan shortens by some fraction every day you spend outside. That fraction can't be precisely calculated because no one has ever lived long enough on Mars to generate the data. You're generating the data now, and you're the long-term study. Radiation kills slowly though, taking years or decades to become cancer. Your own psychology works faster, and Mars has some thoughts about that too. The Mars 500 experiment locked 6 people in a simulated habitat for 520 days to replicate a Mars mission timeline, and the psychological data that emerged tells a clear story. 4 of the 6 participants developed significant sleep disorders. Crew mood and motivation crashed around the 75% completion mark, a pattern researchers call third-quarter phenomenon. Blood tests showed serotonin and dopamine levels measurably declining over time. Not subjective reports, but neurochemistry physically changing from isolation and confinement. ISS data confirms the pattern across a larger population. Between 71 and 78% of astronauts use sleep medication while in orbit. Depression symptoms appear in 35% of men and 43% of women, and anxiety symptoms show up in 23% of men and 85% of women. Interpersonal problems increase 20% during the second half of long-duration missions. Those astronauts can see Earth out the window and hold near real-time conversations with family. Resupply missions arrive on schedule, and everyone knows they're going home eventually. You don't have any of that. Earth shrinks to a dot in your sky, while communication delays run between 4 and 24 minutes, depending on orbital positions. Send a message and wait half an hour for a response, with no real-time video calls and no live conversations possible. During solar conjunction, when Mars passes behind the Sun from Earth's perspective, communications black out entirely for 13 days. Medical emergencies can't call Earth for live guidance. Equipment failures take 13 minutes minimum before Earth even knows something went wrong, then another 13 minutes before their response reaches you. By the 26-minute mark, when you finally hear that help is working on solutions, whatever was happening has already finished happening. Light intensity on Mars runs at 43% of Earth levels, and your circadian rhythm evolved for a different star at a different distance. Martian days last 24 hours and 39 minutes, close to Earth but not identical, and that 39-minute daily drift compounds over time. After a month, you've shifted 19 hours off Earth time, and your body never fully adjusts. Global dust storms cut light levels even further, sometimes for months at a stretch. You stay sealed inside, unable to go outside, watching dim ochre twilight through whatever windows exist while knowing the storm might last another 8 weeks. Your entire social support system consists of 5 other people. You'll see them every day and smell them every day and hear every conversation and argument and bodily sound through thin walls. For years. For the rest of your life. Some people adapt to this kind of existence and some people don't. Psychological screening tries to filter for resilience, but no one actually knows how humans handle permanent Martian isolation, because the 520-day studies only simulated one mission. You're not doing one mission, you're doing all of them, back to back, forever. That's the reality of your life now. You wake up in a pressurized cylinder on a planet trying to kill you through atmosphere and temperature and radiation and gravity and isolation. 2 hours go to fighting bone dissolution every morning. Food comes from crops grown in toxic soil that required chemical washing to remove perchlorates. Water was urine last week. Oxygen gets cracked from an atmosphere that would suffocate you in seconds if you tried breathing it directly. Radiation accumulates invisibly while bone density drops unfelt. Psychological stress builds so gradually that you might not recognize the warning signs until the condition becomes clinical. The nearest hospital sits 225 million kilometers away, and resupply missions take 6 to 9 months. No cavalry is coming, and the emergency number doesn't connect to anyone. You and your crew represent the only humans on an entire planet, and that planet remains completely indifferent to whether any of you survive the night. None of this appears in the colonization pitches. The TED Talks jump straight from landing to thriving civilization, and the animated renders show domed cities with smiling families and children playing in pressurized parks. Nobody renders the 2 hours of daily exercise required to prevent skeletal collapse. Nobody animates the recycled wastewater, or the radiation dosimeters, or the psychological screening that still can't predict who breaks at month 14 versus month 40. That's the fine print, everything you signed up for when you watched the rocket landing video and thought you wanted to be part of this. You're part of it now, the first generation of humans to live on another world. Everything you do carries historical weight. Every problem solved proves something about our species, and every day of survival writes a manual for everyone who comes after. But calling this an adventure misses the point. Adventures have endings where you go home, tell stories, and show photos to people who stayed behind. This doesn't end. This is just life now, smaller and harder and more precarious, measured in oxygen reserves and radiation exposure and bone density scans. Mars is a planet that doesn't care if you make it, and you just moved in. What's the next cosmic death sentence you want the fine print on? I've got some thoughts about what Jupiter's radiation belts do to human nervous tissue, and I'll warn you now, it won't be a long conversation. If you're enjoying my video, please subscribe, hit the like button, and comment below your thoughts on Mars colonization. I worked very hard researching this video, and I'd appreciate any support you can give me. Thanks.